Welcome to a quick lesson on horizontal launches, also known as half parabolas. We have in this situation a pretty typical setup where an object, a projectile, will be launched horizontally and will form a half parabola with its path as it falls to the ground. So there are many problems that match this setup. There can be some variations between them, but in all cases, we should separate our givens into x and y and keep our x-y calculations separate. So for anything that is a projectile, I automatically have as an unstated given that my x acceleration is 0, that my y acceleration is 10 meters per second squared, or 9.8 if we're being exact, down. So I'm going to go ahead and mark that as a negative, because if you're unsure, we could just make down negative and take away confusion on that. Additionally, when it said it rolls horizontally, we don't know how fast it was going, but we do know that it wasn't moving up or down. And in fact, on all horizontal launches, we know that the y velocity starts off at 0. On all trajectories, the y velocity at the top is 0, even as we have some x velocity. Okay, so even before we got to numbers in the problem, we were able to come up with those givens. Let's read a little further and see what else we can come up with. It says 1.25 meters high for our table. So we've got our delta y. The displacement was 1.25 meters down. Now, since it fell down, and since I marked my downward acceleration as negative, I'm going to make my displacement negative as well. It said it strikes the floor at a point 2.5 meters away horizontally. So our delta x is 2.5 meters. Now, the first question was, how long was the ball in the air? So we are starting out by solving for time. And unlike delta x, delta y, or any of my vectors, time could be solved using x or y variables. And so we need to look here and see where we have more information. Well, we have more givens for our y's. And in fact, the equation that has this unknown and these 4 variables in it is VOT plus 1/2 AT squared, which could look kind of daunting to solve that for time, but because the V original is 0, then that makes our equation much simpler. Now, this situation shows up so much with the V original of 0 and the time to go down that if I solve for this time, we get something that shows up as a pretty regular formula, that time down is 2 times the y displacement over the y acceleration. And so if we apply that here, 2 times our negative 1.25 all over negative 10. And here's where being consistent on those negatives matters. And then I have something that I can put into my calculator. So if you haven't already, go ahead and set that up, run your calculation, see what you get. So with that calculation, we can find that that time comes out to, with the numbers that we used, actually exactly 0.5 seconds. Now, when you're on a trajectory problem, if you find yourself stuck and you don't know what else to do, always a good idea to find time, since it is useful for both x and y calculations. And so, speaking of x calculations, our question says, what was its speed when it left the table? Now, I said x calculations. We want to find v original here. That's the unknown. But for any variable, we want to ask, is that x, y, or both? Well, v original has a 0y component. So really the only thing that needs calculation is the original x. And now that we have time to go with our x givens, then we have enough to solve a full equation. Now, with our x acceleration of 0, that becomes a pretty simple equation. And so for delta x equals Vox times time, our Vox can be found simply by taking our x displacement over time. So our 2.5 meters over 0.5 seconds, and that's going to come out to an overall starting velocity then of pretty much 5 meters per second forward. Okay, our last question was, what is the ball's speed when it hits the ground? So our velocity down here when it's not only traveling forward, but downward. So for part C, it's V final. And I just said that we should look at things in terms of, is this an X variable, Y variable, or both? And this one is both. That when it hits the ground, it has some X motion to it, it has some Y motion to it. So we're going to find both of those and we'll combine them. Now the X motion is super simple because we know that V final X equals V original X. If you want more to that equation, well, any of the terms with acceleration in it would zero out, so it just becomes V final equals V original, which for a constant X velocity, that shouldn't be surprising. So our V final X is still 5 meters per second forward. We know that about trajectories, that our X velocity is constant, so once you know it for one point, you know it for everywhere in the trajectory. What about V final for Y? Well, we had originally our acceleration, our V original, and our delta Y. And we have time, but I'm going to go ahead and solve this using only our original givens. And this is just a small bit of wisdom for test situations and others where if I had to calculate a number, maybe I should be careful about it. Maybe I shouldn't assume that I did it perfectly. So given a choice, if we have original givens to go back to, I'll use my V original, my acceleration, and my displacement rather than the time that I calculated. So if I do that, if I take my square root, 4/2 times -10 times my 1.25 meters down, and square root all of that, then we find that we have a V final Y that comes out to be 5 meters per second. So, okay, my X velocity is 5 and my Y velocity is 5. X forward, Y down, and so for 5 meters per second forward and 5 meters per second down, if I want to solve for my hypotenuse, my combined velocity, I'm going to take my X velocity squared and my Y velocity squared and square root them using Pythagorean. And when we do that, we will find a combined velocity of about 7.071 meters per second. So 7.071 meters per second is my magnitude. And that should be ringing a bell there that, oh, well, we have a little more to do because we need to find the direction. And by direction, we mean angle. So to find this angle with our opposite and our adjacent, it's going to be inverse tangent of our opposite, 5, over adjacent, 5. And that inverse tangent, when I plug that in, will tell me that the angle, what we marked up here, and it's always the angle at the start of the vectors. that angle in this case will be 45 degrees. So our final velocity is 7.07 at 45 degrees below the horizontal. Thanks for watching, and good luck. See you in class.